Hello and welcome to the Weekly Space Hangout for Wednesday, February 6, 2019. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about First Science from Chang'e 4, Goodbye Marco, Measuring Martian Gravity with Curiosity, the Milky Way, Totally Warped, Catastrophic Planet Collisions, and more. Joining me this week on my screen is Dr. Kimberly Cartier. Kimberly.
Hey, Fraser, happy podcast day, everyone.
Thank you so much. Who else have we got? Morgan Renberg.
Hey, good to be here.
Paul Sutter.
I'm here too.
And you are in some kind of hotel.
Some kind of hotel near New York on my way from, my various adventures in life.
And the beard looks great, and I want to get some.
Didn't pack a trimmer for this trip, so
yeah.
Going lumberjack, going real.
Jealous of how good you guys can grow your beard.
I can't. The sides of my beard come in really patchy, so this is me over.
Never turn your head.
Yeah, exactly. That's exactly.
I have no comment.
That's right. I've never seen the side of Fraser's face.
Yes, it's just face on. That's all it is.
Face on.
It's like a sphere.
Now,
the way you look, it's all the same.
Now, before we get into our special guest, I want to give everyone a heartfelt reminder that they should take a moment and go to wshcrew.space and sign up and join the amazing Weekly Space Hangout crew. This is the community. This is the glue that binds us together. They are the producers. They are the fan-ducers. And you should absolutely be part of this great community, especially since the place where they formed in the first place, Google Plus, is throwing everything in the garbage. So every post you've made, every connection you've made, it's all going away. And now is your chance to go to the wshcrew.space, sign up, and make sure that you can hang on to this wonderful community of other fans as just the universe continues to move forward. All right. Let's get into the special guest. Joining us this week, we've got Dr. Natalie Hinkel. Natalie, welcome to the Weekly Space Hangout.
Hi, thanks so much for having me. I'm excited to be here.
Oh, you maybe haven't watched enough of these, but we'll see. Who are you? What do you do?
I have watched some of them, thank you. I know how to prepare.
Oh, okay, all right. Wait a minute, I don't think there's any way to prepare for this, but fine. If you think so, then I'm interested to see how this turns out. Who are you? What do you do?
Oh, I like the existential question. So my name is Dr. Natalie Hinkel. I'm a planetary astrophysicist, and that's actually a title I made up because I have a bunch of friends who are geologists, and they make up their own titles to sort of mix and match what they do. And I decided that if they can do that, so can I. So it's a title that means that I look at both stars and planets and how both of them interact in a physical way. And now it's actually an official title. I've seen multiple people with really the title, but I was the first.
But isn't it weird that here we are, however many years it's been since PEG 51B?
25 years.
25. Someone knows the exact number, not counting the days.
Somebody's given talks recently.
Right. Well, here we are, 25 years after the discovery of the first exoplanet, and now there is enough knowledge about these planets that you can ponder their planetary geology-ness and astrophysics. So that's...
And people are still making up words for that. There's like exoplanetology. Yeah. It's I even forgot all of them. Exogeology. It gets weird and more complicated.
I can totally imagine some future episode of Star Trek where they bring in their planetary astrophysicist to solve some key problem on a planet, and no one's going to blink an eye. So I think it's all right that you.
And then maybe I could have a guest appearance.
Yeah, or the Orville. Either one.
I would accept the Orville.
Yep. Yeah, it's one of the best Star Treks ever made. So what does this science that you've invented involve?
Okay, so I look at both stars and planets. So the basic stuff of what I do is that I measure or I take data that measures the elements inside of stars, so like their core composition, and I put together this massive database of the elements that we're able to measure within the stars. And so I can do a few things with that, and the basic one is that I can use a lot of different programming and machine learning algorithms to look at the patterns of those stars, like what they look like in like just in space, like XYZ spaced, or how they're moving, or how they just compare to each other with like rotation rates, stars with planets, stars without planets. There's like so much that you can look at. And then the other thing that I really do is that I look at the stars and planets, because stars and planets are made at the same time. So like essentially the planets are the leftovers after the star is kind of done forming. But so right now when we detect a planet, you can measure a lot of its physical properties, but we currently don't have the capability to measure its composition. We can get maybe a few, and by a few I mean maximum 20 atmospheres. Like we can measure the composition of the atmosphere, but that doesn't tell you what the surface is like, what the interior is like, what it's like to actually be like something on that planet. And so what I do is I work with a number of geologists, and we take the elements inside of the stars and we use them as a proxy for what is likely in the planets, and we build models from the inside out of the planet, so that at the end we get actual like a mineralogy breakdown of what these planets likely look like. And so in that way I try to study like ultimately how stars affect planets, and then how planets affect the stars, because it might also be that by forming a planet it will change ultimately the composition of the star that we're then observing.
And right now, right, like the best that we can do is you can get at the mass of a planet, you can get at the how long its year is.
Yeah, you can get like the mass, the radius, the period, the eccentricity, which tells you how round or not round. Yeah, the density. And I get a little frustrated because people then say like, oh, well, if the planet is at a good distance from the star, it's habitable, it's in the habitable zone. And I'm like, well, that's the physical side of the planet, but you really need the chemical side. Like, you know, we as life, we really like to have oxygen to breathe, and carbon, you know, that we're made out of, and we have silicates that we walk on. And so those are super important for us. And so I think we got to sort of expand that definition of habitability for planets to include its actual chemistry, or at least what we can tell of its chemistry at this point.
And since a lot of this is like right at the very cutting edge of what people are capable of, this is the time when people come up with incredible techniques to really push the scientific instruments to the very limits to try and get some of those clues. And those are some of the research papers that I enjoy the most, is where people are like, oh, we figured out a way that if we could look at the moon that's going around a planet, we could figure out if it has continents on it, or, you know, ways to see that they're interacting. And one of the pieces of research that I know that you did that caused a lot of interest was this idea that the TRAPPIST-1 worlds could have a lot of water on them, too much water.
Yeah, exactly. So TRAPPIST-1 is a very tiny star. Also, I love the name. I don't know if you realize that Trappist is a kind of beer, and it was discovered by Belgian scientists who then like redid this awesome acronym, and anyway, so it's named after beer. So I love it already. So it's this tiny star, and a bunch of planets were discovered around it, and so they're all really close. In fact, all of the planets are at an orbit that's actually closer than Mercury is to our sun. But like 3 of them are in the habitable zone. So then, you know, it came out like, oh, well, they must be habitable. So my colleagues and I, and this is like Cayman Unterborn and Steve Desch at ASU, we started looking more at like the mass and the radius and ultimately the density of these planets. And we're like, those seem a little like light and puffy. So what we did is we took the elements from the star and then put them into this model. And at the end of it, like almost like such a huge percentage of these planets was water or frozen water. So ice. And so I think it was TRAPPIST-1c has 50% or 50 weight percent water. And I think it was B and D had like anywhere between 5 and 15 weight percent water. And in comparison, the Earth has 0.02 weight percent water. So this is like that planet from Interstellar. where it was just like those huge tidal waves and
I recall them walking around on it though. So
way more. Yeah. So it would just be super huge. And so we wrote this little paper saying that you got to be careful saying that these planets are habitable, because on planets, like rocky planets, you need there to be cycles, like geochemical cycles. That's like a carbon cycle, oxygen cycles, silicate cycles that take elements from one place on the planet and shift it someplace else. But if you have all water, then you won't really get plate tectonics. You won't get them moving around. You won't get the cycles that you really need, which means that if there is life, that biome is going to be a super teeny. And then the biosignature of that life would therefore be really hard to detect because it's so small. So we got to be careful about saying like tons of water is good, because it could be that it dilutes the signal.
So, I mean, are geologists like almost driven insane because they know how much is possible to know here on the Earth? They can go over to rocks, they can pick them up, they can watch cycles and processes and continents, plate tectonics, and all of these things happening. And yet, as we mentioned earlier on, you look at other planets going around other stars, and all you know is they exist.
Right. Yeah, they get super frustrated, and that we don't have very many measurements. In fact, there's been sort of jokes that we can't even really say that there's a planet there because we're just looking at pixels and stuff, which is true, but we can get a decent amount of information from a few pixels. So
didn't you do a tweet where you showed people what you actually are looking at when you're looking at the TRAPPIST-1 system? There was like a couple of pixels, and then that's the magic.
It. Yeah, because most of our data, it's not even like as a photograph, it's mostly just data in like wavelength or in different sort of regimes. So it's not even good visually to show people, and you're like, sorry, here's some nice plots that we made. We put on pretty colors.
So where are we then with the state of the technology? What advances are going to be coming shortly with new instruments, new techniques, new developments that might be able to answer some of these questions?
Yeah, that's a great question. So we're going to have, there's James Webb Space Telescope, which has its own issues, but then there's WFIRST, and TESS has launched and is coming down with a lot of really cool data. But with all these different instruments, there's KEOPS. KEOPS is in Europe, which is sort of like the counterpart to TESS. And so they're going to be observing like a huge amount of stars and planets. And so like whereas right now we know, I think it's about 3,800 exoplanets. Most of those by far are giant planets, so like Jupiter and Saturn. But what these missions are really going after are the smaller planets, so the terrestrial planets. And so that can give us like a lot more information on the different kinds of geometries that these planets could form in, which then one thing I would really like to do is then make models of how multiple planets form in the same system, and how the elements like in the protostellar disk, like where those planets are forming, could sort of get sectioned off in order to form these different kinds of planets. So like in our solar system, we have the giant planets are really far away, but the rocky ones are smaller in. So how do we get something like that, and how does that make a difference between the planets that we could form? But as far as the actual like chemistry of the planets, I'm not really sure that any of those are really gonna answer that question. A big part of it is that's holding us back from being able to measure like either the atmospheres or try to get down to the surface is actually the geometry. And so you need to have a star and then a planet and then us, and they have to be perfectly lined up in order for us to see through that. And that's so difficult, especially when we need all of those things, the stars and the planets, to be nearby so we get really good resolution. So having more data will mean we'll get more atmospheres, and that will kind of help. But I'm afraid there's nothing really and I'm not even sure what we could
I mean,
do
is there any kind of link?
technology-wise.
I mean, is there any link between the state of the atmosphere of the planet and the surface geology, or is it just?
There's a little, but like even if you look at the Earth's atmosphere, you know, you wouldn't really be able to tell that, you know, we have a bunch of mountains and stuff. And, you know, with the atmospheres, you have the benefit of biosignature. So, you know, and they talk about this a lot in Star Trek of, you know, oh, they're, you know,
I'm reading a bunch
brass,
of life forms.
Right, and bronze, but also Bronze Age.
Right.
And so Bronze Age is smelting, and you put a lot of heavy elements in the atmosphere that you wouldn't expect to see, and that's totally a thing. That's legitimate science, and so that's something that would be cool, but that's also like that's pretty far off. So, right. Yeah. So what we got right now is pretty much the stars, but I'm really excited to work on models because, as you said, this is really cutting edge. In fact, I think there's like 4 other people in the world who really do what I do. And so it'd be cool to get a few more, have some other people to work with, right. Take some of the work off of my plate because there's so much to do. But you know, that's exciting too.
Well, and that's what students are for, right?
Right. Yes.
Is you grow them and release them into the world.
You water them and you feed them data, and then they produce.
This has always been a field of science.
Right.
Well, Natalie, thank you so much for joining us. Where can people find out more about what you do?
So pretty much everything is my name, and it's spelled Hinkel. So you can go to my website, nataliehinkel.com, and also I'm at Twitter at Natalie_Hinkel, and I'm fairly active on that. At least I'm trying more to be. But yeah, I always encourage people to reach out if you have questions on how to be an astrophysicist, how to get into this for women and minorities. I definitely get that is a hard thing to do, and it's hard to stay in science. So I make it a priority to always respond to students whenever they reach out to me. So, or even non-traditional students, just people who are really excited.
Fantastic.
Yeah.
We need more science communicators.
I agree.
Please, we need more. Anyone? Can we get a little help? But we've got a whole bunch here, and now you have bravely agreed to stick around with us for the rest of the show. So we're going to get into a couple of things. Now we're going to move on to, I believe, Morgan Renberg, who is the top of my screen right now. Morgan, what have you got for us?
Well, this week we got some sad news, which is that NASA has lost contact with the MARCO CubeSats. And if you remember, these are the CubeSats that launched about almost 2 years ago, or I guess about a year ago now in May, with the InSight Mars mission. And they separated from the rocket and flew to Mars independently of InSight, and then observed the InSight landing, relaying back data along the way. And then they didn't go into orbit around Mars, they just shot past the planet and out into a solar orbit. And they continued to sort of go beyond the expectations of mission planners. But this week, they finally, within a week of each other, they finally went silent. And we're not really sure why. There's a couple of ideas have been floated. One is that one of them was having some trouble with its maneuvering thrusters. And so it might be that it no longer could point its antenna towards Earth to send back communications. And if one was having trouble, maybe the other was having trouble as well. We just didn't realize it, and they both failed along the same time. If that's the case, then we'll probably never hear from them again. Another possibility, though, is that their orbit around the sun has just taken them too far away from the sun for there to be enough light reaching their solar panels to power them up enough to keep communicating loud enough for the Earth to hear. And if that's true, well, then the nature of orbits means that eventually they'll come closer to the sun again, and they might wake up and start communicating again. And so NASA has planned a few more attempts over the next few months to try to communicate and see if they hear anything. But even if we never hear from MARCO again, it's been an extraordinary success. Because this is a pair of tiny satellites that were built for less than $19 million, which is basically peanuts on a NASA budget scale. InSight costs more than $800 million. And of course, it does a heck of a lot more. But to be able to do something on such a cheap budget is great. And $19 million got you 6 months flying to Mars, doing useful science and engineering around Mars, continuing off into deep space for months after. It's pretty clear now, and this is not something we knew a year ago, that CubeSats are a viable way to explore at least the inner solar system. And now that we know that, we can start thinking of all of the little questions that maybe we wanted to answer before and think, okay, how can a CubeSat help me answer that question? And then we'll package 50 of them up on a Falcon 9, blast them off, and answer a whole bunch of those little nagging questions that never on their own would have been enough to merit a mission, but in aggregate will open up this whole new way of doing science.
Yeah, one of the really exciting things that I was thinking about is not even just the tiny little questions that don't merit their own missions or their own instruments, but the questions of like, that might be a thing we may want to investigate at some point, but we have no idea if it's actually, a big enough phenomenon to observe there. Let's go explore that.
So what do you think are the limits then?
Like where you can't have like a big enough like justification for a full mission.
Right.
You're flying on a hunch.
You're flying on a hunch.
They're still pretty expensive. They're like $5 to $7 million.
Pocket
they
change.
Are, but these two Marco CubeSats, they cost like what 2% of what InSight costs, and they're pretty easy to just like slap on the same rocket.
That's fair.
I'm
Paul,
exaggerating, but
let me pitch you a mission that you could do with maybe 50 CubeSats that could be interesting.
All right, let's hear it.
Is
that 50 times 7 million?
Yeah, so still we're talking, that's less than a Discovery class mission.
Okay.
Throw in the rocket, and you could do a single pass flyby of 50 asteroids in the asteroid belt and understand sort of a marginally statistically significant distribution in their shapes. And we could use that as a way to check all of these Arecibo observations that we've been making for decades now, and so to line up what we see in a radar signature with what we see in physical form. And we could do that now and then with OSIRIS-REx and with Rosetta and these things, but we do 50 at once. We just sort of take that leap, kind of like TESS, and establish this baseline, and then figure out which of those 50 is worth going to with a Discovery class mission.
And you could really see the situation where they sort of mass producing them, they bring the prices down, and then like if anyone has any question about the solar system, the first thing they do is say, okay, well, let's just send a probe. We'll send a Marco.
Or we finally green light a large Venus mission, and we send a bunch of CubeSats along with it to form a communications relay around a planet that doesn't have a giant set of communication satellites already.
I know a bunch of exoplanet people who would love that because it's really hard to be able to tell if a planet would be like the Earth or be like a Venus, and one's super habitable and one is not.
Yeah, and the fact that Marco was able to communicate back to Earth and to be able to transmit the communications from the InSight lander back to Earth means that you could, if you just sent them out into the solar system as communications relays, that would be an invaluable addition to the infrastructure of the solar system. So that alone, spend $500 million and build a communications, an internet for the whole solar system.
One thing I thought was really cool is at least one of the Marco CubeSats had a camera, and it took some pictures of Mars as it flew past back during the InSight landing. And they're not very good pictures. They're sort of like maybe mid-late 60s quality pictures. But that kind of got me thinking about exactly what you were just saying. If you go back and look at the sort of space race era of planetary exploration, you have Mariner 1, Mariner 2, Mariner 3, Mariner 4, Mariner 5, Mariner 6, Mariner 7, Mariner 8, Mariner 9, Pioneer 1, Pioneer 2. And these are all within like 5 years. And they just did that, right? They sent mission after mission to every planet and then figured out where to go. And I think we have that chance again, not with the planets, we've been there, but with these other objects.
Not barely. I mean, so the issue is like we haven't been back to Uranus and Neptune, right? So we know that, for example, the power requirements at Jupiter, Juno has 25 times the surface area of its solar panels compared to...
CubeSat ain't going to get you to the outer solar system.
Right. So at a certain point, that power system just isn't going to be able to handle it. But it would be great to find out where. Or maybe you can. Maybe you can have solar panels that are, really big compared to a teeny tiny satellite, and you get it, and it fulfills that requirement. A solar sail. That'd be awesome. They should all have a solar sail.
Rode in on, right? Sorry.
Oh,
sorry. You can skip me.
Did you want to get into that? Is that what you want to talk about this week?
No, actually, I don't. I just wanted to make one sarcastic dig and leave it at that.
Well, then tell us what you want to talk about this week, Paul. Since you're on my screen right now.
I want to talk about the Milky Way. And the Milky Way is a barred spiral. We've known this for a really long time. But what we haven't known is the exact shape of that spiral disk. And there are examples out there of spiral galaxies that are very, very flat, and also examples of spiral galaxies that are all wibbly wobbly. And it turns out we just might have a wibbly wobbly one on our hands. We finally got a decent variables. Oh, what?
Your internet. That internet that I said was the best internet you'd ever brought to the table.
From a hotel.
Yeah.
I'll not move.
Yeah.
When I move, it makes it worse.
Yeah.
So I'm gonna grip the table so my hands don't wave around. I'm gonna do minimum lip movements.
Yeah, just your face.
Which sucks because I want to talk about how the shape of the Milky Way.
You be you, man. You do what you got to do.
Okay. So. Researchers used over 1,300 Cepheid variables, which give us very accurate distant measurements to all sorts of points very far away, up to tens of thousands of light years away in the Milky Way galaxy. And using this, they, assuming that the Cepheids fairly and faithfully trace the underlying distribution of stars, they found that the Cepheids were very warped, where one side of them on one side of the galactic disk were above the plane and on the other side were below the plane. So if all the stars and gas in the Milky Way follow those Cepheids, then we've got a pretty warped galaxy on our hands.
What kind of phenomenon could cause that?
There are a few possible mechanisms for warping a galaxy, and probably the most likely candidate it's our barred spiral itself. It's the central bar in the central disk of stars act as like almost a propeller and torque the outer edge of the disk and stir it up and cause these warpings at the edges. It's all gravity.
As usual.
As usual.
I mean, one of the things that's interesting now is we're starting to know like what the interactions of the Large Magellanic Cloud are. For the longest time, people weren't sure what the LMC was going to be doing, and now it looks like it's actually on a collision course with us in the next few billion years. So will we see this get worse as the future unfolds, or will it work out its warp and flatten out again?
Well, it's a little bit hard to tell because, like I said, we see examples of galaxies in both cases. It might be just due to intrinsic stuff inside of the galaxy. So just whatever's going on inside of the galaxy, that can make a warp or keep you flat. It could be extra interactions with satellites or dwarfs or nearby neighbors that cause warpings. Probably a little bit of column A and a little bit of column B. Definitely as we get closer to Andromeda, it's going to get way worse.
Now, is this sort of question something that Gaia could contribute data to?
Oh, for sure.
Cool.
I mean, in this case, right, they did this based on Cepheid variables, but you can imagine, that is, I mean, they're great to be able to tell you where everything is, but when you think about Gaia with a billion stars, positions, and motions, that definitely sounds like the kind of data that they could tease out of that database.
Yeah, the advantage of the Cepheids is they can go really far, so you can really sample the entire galactic disk.
Yeah.
Yeah, because the Gaia data, while it's a huge number of stars, I actually went to the American Natural History Museum this summer, and we projected the Gaia data in the Hayden Planetarium, like onto the dome with like an image of a different galaxy, but it doesn't reach as far as you think it will with all of the stars. I mean, it's a huge distance, and it's more stars than we've ever had, but they're all like relatively near-ish by, and so you got a really good feel for that. In fact, I kind of have an image from that dome on my website because I took a picture of it. There's other data in there too, so some of it's Gaia, some of it's apogee, and some of it's Gaia, because it's chemical data. But like, yeah, we were able to like look at it, which was really amazing. It was part of the Gaia sprint to just analyze the hell out of Gaia data.
So like 1 billion is not enough. 5% is
never enough.
Yeah.
It's right. I mean,
right. That's like less than 1% of the stars in the Milky Way, and they're all preferentially clustered very close to us. So it's not an even data set.
Is it like
they never are?
Is it green? Is it like the galaxy and there's like a green blob in the middle of it?
Yeah.
Okay, hold on. Let me just...
And I that might not be all the stars, but it's like a subsample of the stars because we were actually tweaking out the program. But yeah, that one.
Yeah.
That's
pathetic.
Oh.
No. Come on, Gaia.
Don't be hating on Gaia. It's awesome.
And I think a lot of that is sub-selected to have apogee and Gaia, but that still reaches like pretty far. But yeah.
I've mentioned in the past we could just make this the Weekly Space Gaia show if we wanted to. Like, we could just talk about Gaia every week, and some interest, like, if you look through Astro PH, like half of it is papers from Gaia, because they're like, oh, here's all the white dwarfs we found, here's all the dwarf galaxies that we found, here's all the red dwarfs. Wait a second. So we got into a conversation before. Did you want to just bring this up so that you can school us on this before we get into Kimberly's story?
Okay, so I will preface it by this. I got my PhD 2012. So the term red dwarf was never a term that I learned that I ever used, that anybody I know actually uses. We just say M dwarf or K star, K dwarf, but red dwarf isn't really a thing that scientists use. It's not really a phrase. And whenever anybody says it, I think of like the old BBC show with like this, everybody, there's like a hologram, there's a cat who is so old that it evolved to be like this crazy awesome human. Like it's that's what I think of when people say red dwarf, and Wikipedia has it wrong. So if anybody has time and cares, could you go change it to say M dwarf, please?
Can't you just do like some kind of copy paste? Like some kind of recursive copy paste, and you would, of course, completely mess up the show that you were mentioning, right?
I know.
But you would also fix all of the improper use of red dwarf stars.
And then if I get it wrong, and then it'll undo all of my changes.
They'll do that even if you get it right.
It's true. I know, because I don't have a login account, so it'd just be this random IP of like, I hate this.
No, thank you. I hate this. Kimberly.
Yeah.
Something less controversial.
Mars. It's not my favorite planet in the solar system, but that's okay. Because one of my favorite things about a lot of space science missions is when the scientists can figure out some clever way to use a rover or a satellite or a data set in a way that it was never intended, and come up with some really awesome scientific results. And that's exactly what happened recently with Mars data from Curiosity from the first 5 years that it was roving around Gale Crater. And what the Curiosity scientists did was they looked at some of the roving, the data from the engineering data set from the accelerometers on Curiosity, which help it navigate around Gale Crater, and they were able to repurpose it to measure the gravity of Mount Sharp as Curiosity was slowly climbing the surface. And what they were able to figure out from that was what gravity from Mars's surface Curiosity was experiencing as it was slowly ascending this mountain, which let them measure the density of the rock in Mount Sharp. And what they found was that the rock was actually a lot less dense than they were expecting, which means that it's more porous, it's lighter, which has some interesting implications for how this mountain may have formed based on the fact that it's a lot less dense than we previously thought. And it's a really fun thing to delve into an engineering data set and come up with a really profound scientific conclusion from it. That's not a data set that's often used. It's not one of like the flashy data sets from all these rovers or satellites. It's like the back end calibration data sets, and you get some really cool science out of it. But also being able to measure the gravity of this mountain as the rover was slowly going up, like something like 700 different data points, like minuscule changes in the amount of gravity, is pretty astounding.
I mean, is this something that someone just said, hey, I know something that we could do with the accelerometer on board Curiosity, or was this always part of the plan?
They were inspired by one of the old Apollo little, not really a rover, but it was like driving around on the surface of the moon, and they had a buggy. Thank you. They had a gravity measurement instrument on that buggy as it was roving around the moon, but that was a dedicated gravity instrument as they were doing that, and they were able to get gravity measurements as it was roving around the moon, and that's sort of where the idea came from. But Curiosity is not equipped with that particular instrument, and so they wanted to do a similar measurement and figured out a way to do it. I mean, the accelerometer was built to measure the acceleration of the rover as it was moving around to figure out where it is, and to figure out elevation changes. And elevation changes can also tell you how the gravity itself is changing.
So what's really cool about this is that if you actually look at the data, the accuracy of this sort of backwards derived estimates that they got from Curiosity is about the same accuracy as that dedicated experiment on Apollo 17. And so we've skipped forward 48 years, but now sort of by accident we can discover things that were state of the art back during the space race. And it really does sort of change how we look at Mount Sharp, because this is a mountain, one of the largest mountains on Mars, in fact, that's in the middle of an impact crater. And that's like a weird place for a mountain to be. So the old thinking was basically that impact crater happened, totally filled up with soot and debris and stuff, and then was eroded away over billions of years to leave Mount Sharp. But as Kimberly says, if that is what happened, all that weight from a 200-kilometer impact crater would have crunched down the rock to be much, much harder. So instead, now we think that Mount Sharp was actually built up layer by layer over a very long period of time. And in some ways, that's like even better, because it means that it's recorded hundreds of millions of years of Martian atmospheric and geologic history layer by layer, in much the same way we might go to an old mountain in the United States to look and see what was happening on Earth hundreds of millions of years ago.
And so instead of the whole mountain forming as this gigantic splash when whatever asteroid crashed into it, you've got a situation where it actually built up over time, and you've got this history layer by layer. That's amazing. That's the conclusion.
Yeah, and of course other rocks will have been mixed in. Like the rocks it pokes on the surface are a lot denser. They're like 50% denser than the rocks that it's just driving over. And that's why they stuck out, because they were bits of harder rock that got mixed into these agglomerated rocks.
Kimberly, what kinds of questions would you be able to, I think, would you also want to be able to answer about the densities of these kinds of features on Mars? I mean, we know what they're like on Earth. We got the comparison from what they did with the moon, and then you've got this situation on Mars. What would people be looking for, but differing between these worlds?
Well, I mean, like Morgan said, we want to be able to, we hope to be able to measure differences in different layers of rock like we can here on Earth. And what that can really tell us is the different chemistry, the different, like he said, the different atmospheric composition. It can tell us whether there were particular impacts or natural disasters that happened at any particular time. It could tell us about the water and whether there was any sort of biome at that particular time, if that got mixed into the rock. It can tell us things like whether surface rocks were able to be mixed in deep within the Martian surface at any time. If we get a better understanding of the tectonics, we can figure out what the remixing of the rocks what the cycles of the rocks were, which, as Natalie told us, is very important for habitability.
Yeah, very cool. All right, so now we've got 2 exoplanet experts this week, and I'm gonna wade into a story, and I'm gonna get it all completely and totally wrong, and I'm just gonna eject very quickly. So
slowly back away.
Slowly back away. I'm just gonna show you a really cool picture here. Hold on. All right. So, and I'll show my co-hosts the picture as well, so we can all just check this out. So this is an image of a collision that is thought to have happened in the star system Kepler 107. And so in a astronomers, the Kepler catalog, there are many, many planets in the catalog, and the 2 worlds in the Kepler 107, B and C, have really strange densities. So the one of them is, and I forget the number here, like 5, what was it, 13? One was like 13 grams. One was incredible, like made of iron, and one was really, really light. And so the thinking that's happened is that possibly we're seeing the aftermath of a collision, a planetary collision that happened in the Kepler 107 system, and actually seeing the wreckage that happened. How long ago? Relatively recent to be able to have this kind of breakdown between these 2 worlds. And so, this feeds into this idea of, like, back in the history of our own solar system, there was a lot of movement of the planets and that things crashed into each other. We see that, the thinking is that Earth was crashed into something Mars-sized, generating the moon. And so to be able to see worlds out there that seem to have some kind of indication that there was a recent collision is pretty exciting. And as we get more and more views out there, as we see a larger survey. Okay, there you go. Someone just put into the chat. So Kepler C is twice as dense as Kepler B. And, we just lost the number there, because this was the part that's interesting. So 12.6 grams per cubic centimeter for Kepler C and 5.3 grams per cubic centimeter for Kepler B, which I think is pretty close to Earth, right? We're around the 5 grams per cubic centimeter range here. So to have something that's that dense is kind of amazing. And so the thought is that between this collision, one turned into the sort of iron ball, and the rest was shredded out and pushed around. And then you got these interactions with whatever was in the solar system disk to separate these worlds out again. So pretty fascinating.
Yeah, and these 2 particular planets, they're approximately the same size. They're both sub-Neptune, and they have about the same radius, but the big difference is the density. And given the composition of the star, you would expect that the 2 planets that are so close to each other in orbit would probably have pretty similar compositions and densities. And given they're the same size, their masses are certainly not the same, and their densities are certainly not the same. And that's sort of the big clue that maybe something big has happened in this system. Plus the fact that they are in an almost resonant orbit, which doesn't tend to happen without a lot of movement to get things to settle into the right place. And moving things around shifts things gravitationally, could cause a big impact. We know that, but I don't know that there would be any way to actually firmly tell whether this is the result of a collision. It's a good explanation for the density difference.
That's always a rub with exoplanets.
Yeah.
It's a great explanation that would explain the difference in density. Something like the stripping of the surface from extreme ultraviolet would not do something like this, because the outer planet is the one that is more dense and would have had to experience more surface stripping of the lighter silicate materials, the mantle materials, which isn't how it would work. If it was because of stripping from extreme solar light, the inner planet would experience more of that extreme ultraviolet and would end up denser than the outer planet, and it's flip-flopped.
It's
It's
in
a good explanation.
In the YouTube chat, James Dubbin says that lead is only 11.3 grams per cubic centimeter. So one is denser than lead. Of course, you get gravity pulling the whole thing together, and that makes it higher than what you would expect if it was just a block
but
of
not
lead.
too much gravity, because if there's tons of gravity, then you could say that maybe it was like a collapsed star that had like shrunken down to like the size of a planet. But then we'd see is like some weird gravitational things, which doesn't seem like we are. In fact,
and the star would
the
be
weird
orbiting
stupid metaphor. The metaphor that's coming into my brain is from The Sandlot, where when the main kid knocks the not Smalls, but the kid who's really great at baseball, he knocked the guts out of the baseball
hard.
So that's the core of the planet, and that's what we're seeing, and it ripped off all the lighter stuff, so that was the shell, and so that's like on the outside into the other one.
And you wish that you could have some other way to find any more information at all apart from just a vague, interesting paper, and then we just move on looking for more examples of this.
Well, Natalie, I was going to say I had an idea, and I was wondering if you could give your thought on it. Was if this is a result of a collision that happened maybe not too long in the past, if there would be some evidence in like exozodiacal dust left over in the system from the collision.
Yeah, that would definitely be something to look for. So then you'd need to look at like in the wavelengths where dust would really glow, so infrared, and that would be a good place to check for to see if there's a debris disk essentially with the aftermath. I think that's a great idea. But also getting back to one of the question that Fraser asked me earlier, which was about technology, it was like, let's start doing some speed of light stuff so we can get some satellites further out, like way outside of our solar system, and like.
But isn't this maybe a way that you can get at that, some way to see the geology of other planets is just like look for ones that smash together. And so you can just see for a moment what they're made out of, as you said, baseball that's had its gut smashed out. Then you briefly get to see what's inside the baseball.
Actually, there are a few people doing something like that.
Yes.
Yeah, but it's planets that were like swallowed by a white dwarf, and so they get stripped apart. And so that's cool because you can see the internal composition, but man, it's super hard. So Mike Jura, who actually passed away somewhere recently, he's a great researcher, a really great guy. He started doing this with like white dwarfs and swallowing up planets and just like stretching them out, and then their elements actually will like land on top of the white dwarf, so you can actually measure them even directly be at that. But there's not like a ton, but that is the closest thing we have right now. It's just
and I think there are maybe 3 of those kinds of stars in the Kepler and K2 catalogs that are essentially the leftover rocky cores of planets that used to be a lot bigger, and because they're so close to their stars, they're just getting stripped away and it becomes this giant planetary comet. So they're thinking about it, and you need something like a giant mid-infrared telescope, maybe the size of a tennis court, something like that, to study it.
Right.
Some unnamed telescope to launch sometime.
I've heard one is going to launch in the year 3000. I did a story on this, so I think I mentioned, it's going to launch in the year 3000. All right, Morgan, we've got one last story from you before we wrap things up.
Yeah, this is a quick one. A few weeks ago, we were talking about the landing of Chang'e 4 on the far side of the moon. And this is a Chinese mission that placed a lander and the U-2 rover on the surface of the moon. And they took some pictures and then almost immediately went to sleep because it was going to become lunar night on the far side of the moon, and the temperatures would drop hundreds of degrees, and they needed to conserve energy basically just to stay alive. Well, it's daytime again, and they woke up and returned their first little bit of science, which is already sort of validating the value of going to the far side of the moon. And that's that they took some temperature measurements of the loose soil on the top layer of the moon, and they found that the temperature there was notably different than the temperature measured in the same sort of geologic regions by the Apollo astronauts. And what these scientists are speculating we're seeing is the fact that the surface is a different composition. and therefore it's retaining heat in a different way. And I would expect this to be the first of many small deviations that we add up from the Apollo results that will paint a different picture of the far side of the moon.
There's a couple of things that I just want to show before we wrap things up here. So the first thing here, I'm going to show my co-hosts so they don't know what I'm talking about. So this is the NASA's Lunar Reconnaissance Orbiter took a picture of the Chang'e 4 landing site. And there it is. Can you see the arrows right there? Right there.
Right there.
And then we'll zoom in right there. And there
Tiny little lander.
There's the
Hello.
lander. And I guess
Hi.
the rover's around there somewhere.
Aww,
Yeah.
cute.
Yeah, isn't that great? And
What's
then,
hilarious
So tiny.
about the rover is that it has to go to sleep when it's too cold out. It also has to go to sleep when it's too hot out. The lander can keep working during the whole 2-week day, but the rover has this narrow temperature band that it can operate in. So it only basically works like 4 days out of every month because it's either too hot or too cold. So it's got to wait for the sun to get sort of a grazing angle, and then it'll wake up again, take some more measurements, and then go back to sleep for 2 more weeks.
One would think that they would have known that ahead of time. That,
Well,
you know,
I think they did,
Yeah.
and they just
sometimes
figured,
the
hey,
moon is always bright and sometimes
we'll
it's
work
dark.
4 days a month and just take it slow.
so here is another picture, which is
impatient.
just great. That was just released today.
That picture's great.
Just
Oh, I love
amazing.
this picture.
So this is
That one.
taken by the relay satellite, and you can see this is the far side of the moon, and then Earth just down in the bottom corner here.
Hey, that's me.
Everyone on Earth is in this picture.
Paul's
no,
there too.
half of the Earth.
Yeah.
And you can see the permanently shadowed craters at the top bit there. Yeah, kind of.
That's pretty awesome.
Yeah, it's
That's amazing.
Yeah. So congratulations, China. You did it. And keep sciencing. Sorry about those plants.
Yeah, they
All right.
were there for a little
Them
bit.
Kimberly, you're on my screen right now. Tell us something
Hi.
interesting that you're working on.
Ooh, so I'm working on something right now about the melting glaciers in Arctic Canada, revealing hidden landscapes, which is fun. And then
It's not
I
fun.
will be
It's terrifying, and it
it's
fills us with
terrifying.
existential
we
dread.
shouldn't be happy about melting glaciers in Arctic Canada, but we do get to study plants that haven't seen daylight in 40,000 years. So that's kind of cool in a really terrifying and alarming sort of way.
Right.
So that's what I've been working on this week.
Uh,
You can
Morgan.
read all about it on eos.org.
Yay. Morgan.
Well, if you didn't get enough of rampant dark energy destroying the very fabric of the universe last week, I have a great video coming out on Friday over at SciShow Space that is going to dig into that a little bit more. We should all be okay, but don't take anything for granted.
I was worried.
I'm going to promote the exact same thing, which was that my video this week was talking about the changing nature of dark energy. So you should check out that on my YouTube video, featuring a cameo by Paul Sutter. I don't know if you know Paul, but you cameoed.
I didn't know. What'd I do?
The clip where you talked. We actually put the clip from last week's Weekly Space Hangout where you said it's probably not right because it's cool. And I use that as a way to sort of just, I'm going to add that to every video that has really cool
that
news.
Works. And you mentioned that popped up on your Twitter feed. Now it's Sutter's first law.
Yeah. So one of my YouTube commenters, Twirl of the Mists, said that we should call this Sutter's first law. If it's interesting, it's probably wrong.
Probably wrong.
Yeah. So there you go. I don't know how many you get. Do you get 3 laws?
You can get up to 3,
Right.
Between 1 and 3 laws.
Right. So you've got to decide if you want to fill the first slot with that one. It's
that.
a good
I'll
one.
take that as my first law.
Yeah. I mean, you can rearrange them in any order you like.
I mean, it's just 3 laws. It's not necessarily ordered.
Right. Yeah.
Like the 10 Commandments, just 10 things.
But while
Those are ordered.
But while I've got you here, I've actually got you on my screen right now, and I think people should get used to this. You and me, close to each other. We are going to be in June. We're going to be at Joshua Tree with the All Stars Star Party.
Love it. Yes, the end of June, go to astrotours.co. That's astrotours.co/allstars. And yeah, it's a huge party in the desert, at a resort, having tons of fun during the day, going out stargazing every single night for a long weekend. It's just fun for the whole family. And it's during the summer, so you can bring the whole family.
We're going to have telescopes, we're going to have adventures, and we're going to teach you the night sky. It's going to be a lot of fun.
Yeah.
So astrotours.co, you can find out more and reserve and join us. Do you have anything else that you're working on, Paul? Oh, his internet cut out. We'll just wait. Try again. Yeah.
I'm here.
Yeah.
I got nothing else going on. I'm pretty bored, actually.
Okay. There must be something. Book, trip.
So book tour starts in a few weeks. Check your local listings. I'm still on the Science Channel, How the Universe Works, every Tuesday night. That'll be fun. The book is still for sale. Go to Amazon.com. Your favorite bookstore nationwide.
I don't have one at arm's reach. I apologize. I'm assuming you didn't take one with you yet. All right. Natalie, you get the final word again. Thank you so much for joining us. Where can people find out more, and what's something really cool that you have worked on or might be working on right now?
All right, so the super coolest thing I'm working on now is a machine learning algorithm that's like Netflix, but instead of predicting which movies you love, and I love sci-fi and goofy comedies and stuff like that, I look at the elements inside of stars that we know host planets and use that to predict which stars are likely to host planets. So that paper is in the works. I'm working with referees and editors, so it should be done soon, and I can even let you guys know as soon as that bad boy is done.
I'd watch that show.
Yeah, it would be really good, and then you get planets out of it too, so it's a win-win. So people, I'm going to be at Emerald City Comic-Con. That's in March, and I'm having a panel there where it's for my podcast, The Science Bar. So we get drunk and talk about science news. So it's like drunk history.
Sounds like a better version of our show.
Yeah,
it's
we never thought about getting drunk and then doing this show.
Oh, man.
It is great, but it does require some editing afterwards to make sure that we actually said what we meant to say. So that's always fun. So normally it's me, a geologist, Craig Hardgrove, and two improv comedians, Chrissy and Dorian Lenz. But in Seattle, it will have like some more local scientists, so like Jim Davenport and Charity Landers. And yes, you can find me there. And that I also have an interview on Sci-Fi Wire during Emerald City Comic Con, so that'll be awesome. So
sounds great.
Yeah, my Twitter is the best place to get to me.
All right, I'm going to put us all back in the gallery view so that everyone can see us. I'll let you guys see what this looks like.
Called the Brady Bunch view, Fraser. Come on.
This is Inception. Hold on here. That was too far. All right. Well, big thanks to everyone for watching us. Thanks to, of course, the Weekly Space Hangout crew. Thanks to all of the moderators, everyone participating in all the chats. I apologize. I saw people were like, how come Fraser doesn't bring in all the chat stuff? Just busy. We had a lot to talk about. I'm sorry. Next week, I promise. And thanks to our special guest, Natalie. It was great having you on the show, and I can't wait to find all those planets.
Same. Thank you.
All right. We'll see you all next week.